speaker of this afternoon will be Francis Thackeray, who is a Phillip Tobias Chair in Palaeoanthropology at the Evolutionary Studies Institute at WITS. WITS stands for the University of Witwatersrand in Johannesburg, South Africa. And Francis will talk about human evolution in Africa, a probabilistic definition of a species, and Sigma taxonomy. Francis is a South African who made his studies partly in South Africa, in Johannesburg, where Dr. Brenner is from, and he made his PhD at Yale University, followed by studies and work at different research institutions and museums, including the Natural History Museum in Washington, if I'm correct, Francis, the Natural History Museum in London, and of course in South Africa. And of course he is one of those paleoanthropologists whose name is closely related to one important place on Earth, the cradle of civilization, the cradle of humankind. In South Africa, close to Johannesburg, Stankfontein and Kromdraai, where Francis has made significant seminal and pioneering discoveries regarding our origins. But Francis is not only a scientist, he's also a poet who writes poems. Well, he has good reason to do so, because Francis is the 9th order great-grandson of a person who is seen here, William Shakespeare.
Professor Sidney Brenner, Professor Bala Skoulias, Professor Jan Vospinder, Professor Benjamin Seat, Dr. Padmana Ban, Professor Svante Pabo, staff and students of Nanyang Technological University, distinguished ladies and gentlemen, it is a great honor for me to come from South Africa to Singapore by plane across the ocean to participate in this inspiring lecture series on the Chronicle of Evolution, initiated by Professor Sidney Brenner, a fellow South African from this university and a Nobel laureate. Thank you. I am most grateful for the welcome which I've received here at the Nanyang Technological University, which is clearly at the cutting edge of scientific research, as reflected, for example, by what I have seen at the Cognitive Neuroimaging Center. There you are studying human brains with extraordinary high resolution. In South Africa, we are studying the brain endocasts of fossils that represent distant relatives of all humankind. Both in Singapore as well as in South Africa, we are obtaining exciting results, and it is a great pleasure for me to talk to you today about some of the exciting results that relate to human evolution in Africa, the cradle of humankind. So my acknowledgements are immediately to Professor Brenner, to Professor Ballas, Professor Jan Vospinder, and also to my colleague in Johannesburg, Professor Peter Vale from Johannesburg, who is associated with the NTU. And it was through Peter Vale that I was introduced to Ballas at the Stokefontein Caves, where we find fossils going back more than 2 million years. And we had a very stimulating discussion about the brain in human evolution. The brain. Ballas studies modern humans with great precision. Of course, you've got the original soft tissue in the brains in modern humans. We in South Africa have not fossil brains, but we have endocasts. Sand has fallen into the skulls and been calcified by limestone, and we have very good endocasts. This is a fossil called AUSTRALOPITHECUS africanus. Australo from the south, Pithecus meaning ape-like, and of course Africanus from Africa, the ape-like creature from South Africa, described in 1925 by Raymond Dart, a close colleague of Professor Sidney Brenner. They both had something in common. They had sparkling eyes, and they spoke about science with passion. I knew Professor Raymond Dart, and I got to know him as someone who was interested both in scientific research but also in teaching evolution to young scientists in the making. And that's what I see here today in Singapore. The Taung child, that's what it's called. Taung, T-A-U-N-G. The place of the lion is situated just southeast of Johannesburg. This fossil is about 2.5 million years old, Australopithecus. It was the first fossil of its kind to be described, confirming what Charles Darwin had said, that Africa was the cradle of humanity. Charles Darwin had looked at modern primates. He looked at the great apes. He looked at orangutans, skulls and skeletons. He looked at human skulls and skeletons. He looked at chimpanzees and gorillas, and monkeys for that matter. And he recognized that of all the living primates, it's the chimpanzee and the gorillas that are most similar to humans. Darwin went one step further, and he said, well, chimpanzees and gorillas are found today only in Africa. And then Darwin, who was very perceptive, concluded that Africa must have been the continent from which humanity evolved. That was a statement that he made in 1871 in a book called The Descent of Man. It's been confirmed that Africa is the continent from which humanity evolved through the discoveries of fossils of Australopithecus, like this one, and also, most recently, fossils like this, which have been called Homo, and this, in my hand, is Homo naledi. Homo naledi has been in the news recently because my colleague, Professor Lee Berger from the Evolutionary Studies Institute, has now found 18 individuals of this new species, Homo naledi, which we now know to have lived about 300,000 years ago. Fossils like these have confirmed that Africa is the cradle of humankind. Oops. Sydney, we have your photograph on the walls of the University of the Witwatersrand, together with photographs of Nelson Mandela, Aaron Klug, and Nadine Gordimer, fellow Nobel laureates. If you were to come to WITS today, you would see your photograph in many of the buildings and institutes on the campus. We in South Africa are very proud of your achievements. To turn to the title of my talk, Human Evolution in Africa, I've already given you an introduction, and a probabilistic definition of a species. One of the crucial things in paleontology is classification, taxonomy. How to classify the fossils into one or other species. But boundaries between species are not always clear. And that's what I want to talk to you about in the context of what I've called sigma taxonomy, where sigma is the Greek word for S, which relates to spectrum, the spectrum of variation through time and space, as opposed to what's called alpha taxonomy. Alpha taxonomy is what we've been doing for decades, centuries, if you look at what Linnaeus did. He recognized that modern fauna, modern animals and plants can be classified in the genus, for example, Homo, the genus Homo, and the species sapiens, Homo sapiens, representing us. And of course, we can apply that approach to the fossils, as we've done for the TAUNG child, when Raymond Dart called it Australopithecus africanus, with a sample of 1, it was easy to create a name for a new species, Australopithecus africanus. Then as work has gone on for more than a century, we have fossils that represent early Homo. And as we get more and more fossils, we have more and more species. Currently we have about 24 hominin species that relate to distant human relatives. 24. But now we have a problem. As the sample sizes increase, the boundaries break down. And the thing that I find so exciting at the moment is that the boundary between Australopithecus and Homo is also a bit fuzzy. It was Alfred Russel Wallace, who knew Darwin, of course. It was Wallace who spoke of fuzzy boundaries between species. That was in 1870. Fuzzy boundaries. That's the problem that we currently have in paleoanthropology, because the boundaries are becoming blurred. And what is needed, as far as I'm concerned, is a probabilistic definition of a species. So instead of using alpha taxonomy, whereby you take a fossil and put it into box A or B or C, clearly defined, instead of that, you use sigma taxonomy, whereby you try to assess probabilities that specimens do or do not belong to the same species. Let me give you a brief introduction to Darwin. Here he is on the left as a young boy, 7 years old. That was his first connection with South Africa, because he's holding a pot with a plant in it that actually comes from Cape Town. His father collected plants from all over the world, and that is the Cape cowslip. On the right, you see a young Darwin in about 1836, when he traveled around the world on a ship. This ship, the Beagle. He went from England to South America, to Australia, Sydney, and then he came to South Africa in 1836. And you know what? He took an ox wagon and he crossed the Cape Flats, and he said, what a dull country South Africa is. I have never seen such a more dull and uninteresting country. That was his first impression, which he wrote down in his notebook. But then he learned of the animals on the other side of the mountain, and he said, eventually, he recognized that of all the countries in the world, South Africa was the most notable for its large quadrupeds. Other statements that he made, even after 1837, when he returned from his trip around the world, he came to the conclusion that one species could change into another. But he said, it's almost like confessing a murder to assume that one species changed into another. That was in 1837. In 1850, he wrote to a botanist, Joseph Hooker, and he said that classification would be easy were it not for confounded variation, recognizing that boundaries were breaking down. In The Origin of Species, which he published in 1859, he had nothing to say about human evolution. That was too sensitive. But he did make one comment, and he said, "Light will be shown on the origin of man." In 1871, as I mentioned earlier, he recognized that of all the living primates, it's the chimpanzee and the gorilla that are closest to humans. And he went on to say, Africa is the cradle of humankind. And he recognized that chimpanzees and humans must have had a common ancestor. Well, remarkably, fossils have confirmed what Darwin had said in 1871. That common ancestor for a chimpanzee and a human probably goes back sometime between 6 and 10 million years ago. That's based partly on genetics. But now we have the fossil evidence, like the TAUNG child. The fossil on the left is the TAUNG child, described by Professor Raymond Dart in 1925. And on the right is another fossil, which we have called Mrs. Ples, also Australopithecus africanus, discovered by Dr. Broom. Well, going back to Charles Darwin, he wrote in a little notebook in 1837 his first evolutionary tree. And as you can see, it starts at the bottom with the number 1, and then it branches out, and there's an A, bottom right, and then above it there's a B, but the B is closer to the C. He was beginning to think about phylogeny, the way we classify through time. This is something else. You can see, I think, there again. And this is the situation in 2008 when there were less than 20 species that were formally described. Notice you've got time on the y-axis going up and down within the last 4 million years, but there is no scale on the horizontal axis. No scale whatsoever. That's typical of the trees that are drawn by paleontologists to this day. They just draw time on one axis and then some sort of branching relationship, which is always controversial. Who's related to whom? But now, we have yet another problem. Where is the boundary between Australopithecus on one hand and Homo habilis on the other? Homo habilis was a species described by Louis Leakey, Phillip Tobias, and John Napier in 1964, in the early exciting days of paleoanthropology, when I was a young boy in South Africa, allowed to collect fossils at Sterkfontein with the assistant of Robert Broom. This is the situation now. Where is the boundary between Australopithecus and Homo? Very quickly I'm going to describe the kind of thing that I've tried to do. This is yet another tree, a phylogeny, which was updated by myself and Gina in 2016, last year, based on Bernard Wood. And you can see it's not a straight line. You don't go from Australopithecus africanus to Homo habilis, to Homo erectus, to Homo sapiens. There are lots of branches. Now we have 23 to 24 species in the family tree. It's not necessarily a tree, it's more like a bush. The spectrum of time on the vertical axis, but again, no scale on the y-axis. And that's a problem. Where are the boundaries between species as sample sizes increase? We now have more than 3,000 hominin fossils in collections from Africa, from Europe, from Asia, and it's become a little bit bewildering to pigeonhole fossils into one or other species. The boundaries are breaking down, just as they did for Charles Darwin. Charles Darwin, before he published The Origin of Species in 1859, he described barnacles that you find on the shores of the sea. And he found exactly what we found today with hominids. As he increased his sample size of barnacles, species A wasn't necessarily so clearly different from species B, and B wasn't so clearly distinguished from C when samples increased. So what I have done is to develop a mathematical approach whereby you can address the problem of classification, especially when it applies to fossils. Here is a map of southern Africa showing the area in purple of the cradle of humankind. It was declared in 1999 as a World Heritage Site by UNESCO. And there is Raymond Dart when he was a young man in the Department of Anatomy, medical school at the University of the Witwatersrand, with a photograph of the TAUNG child soon after it had been discovered. There's Raymond Dart as I remember him. Sydney, can you see the sparkle in his eyes and his sense of humor just like yours? And it was wonderful to, as a teenager, talk to Raymond Dart about the discovery. And he was still, even though he was probably approaching 90, he was enthusiastic as ever, just as if he'd found the fossil the day before. Well, this is the area of the cradle of humankind where I've worked. I've worked at the site in the middle called Stukfontein. I've also been working for 25 years at Kromdraai, and I've also worked at Swartkrans. Those are sites situated very close to each other, only within a few kilometers of each other, in dolomite. Dolomite is a rock in South Africa going back 2 billion years. 2,000 million years, when there was a shallow, salty sea in that part of South Africa, and the water was rich in calcium. The rock from which the caves are formed is this dolomite, and caves are formed underground because the calcium carbonate, the limestone, is dissolved by water percolating through the rock. So you have underground caves, sometimes with little chimneys going up to the surface. Sand falls down through the chimney into the chamber and is deposited as a talus cone. But then you can have travertines formed, the calcium carbonate limestone deposits. And then you can have episodes of deposition and erosion. So stratigraphy isn't horizontal, it's more complex. This is Stukfontein with its cave system, and there is my colleague Professor Ron Clark with a replica of a fossil that was found in 1936, just over 80 years ago. The one that was called Palaeoanthropus by Robert Broom. On the right, you see a replica of Mrs. Ples. Mrs. Ples being the nickname for this fossil, the skull from Palaeoanthropus, which means almost human. And Robert Broom assumed that the skull was female, based on the sockets of the canine. And unfortunately, all the teeth were broken. But on the basis of the sockets, he said, it's female. So it was called Mrs. Ples as a nickname. Robert Broom went further to say it was adult because he recognized that the sutures apparently appeared to be closed. There is Mrs. Ples from the Diepsong National Museum of Natural History, formerly called the Transvaal Museum, discovered by Robert Broom in 1947. 70 years ago, we are celebrating the 70th anniversary of the discovery of Mrs. Ples. And as you can see, the skull has been broken. Why was it broken? How would it be possible that somebody could excavate such a beautiful skull and break it? Well, Robert Broom was working with dynamite. He was working with the miners who were digging for calcium carbonate in the 1940s, and after an explosion and the dust had settled, there was the skull. You You can see the base of the skull there, where Robert Broom is pointing, and top right is the skull cap, which is unfortunate. And there's my friend John Robinson, whom I knew when I was a little boy in South Africa, with Robert Broom, looking at the skull now lifted out of the matrix of calcified sand, which we call breccia. But perish the thought, Robert Broom was using a hammer and a chisel to knock the rock away from the skull. It's not the way we work these days. These days we use a little drill or ascribe to remove the sand grains slowly and carefully. And when Robert Broom was using his hammer and chisel, he must have said, oops, because he'd removed part of the skull cap with the rock. And I discovered these 6 fragments of rock with cranial bone attached. I found them in a box in the museum store. And the box was labelled rock associated with Mrs. Bliss. I was thrilled, and guess what? I went back immediately to the vault, which we called the Broom Room. And in the Broom Room, I could put them back onto the skull because the cranial bone was still retained. But now look really closely. Just in the middle of that rock, you can see a layer of calcium carbonate. And that was very crucial for trying to date the fossil, using magnetic properties in the rock. We used that photograph of Robert Broom on the day when it was discovered, on April the 18th, 1947, 70 years ago. We could see from the photograph the back wall. And we then took magnetic readings. We registered what was magnetic north, having reconstructed the orientation of the skull of Mrs. Bliss. That red line marks modern magnetic north. There's that horizontal line in the block of rock, which we could relate to that photograph taken in 1947. On the basis of the magnetic properties of the rock showing normal polarity, we could say Mrs. Bliss was at least 2.1 million years. Now we know that it was closer to 2.6 million years. And furthermore, we did pioneering CAT scans of Mrs. Bliss. Even though the teeth were broken, we could see the roots using computed tomography, CT. We were among the first to use CT scanning technology to look inside the skulls, non-destructively. There you can see the roots of the premolars, the 2 dots which are closely associated, and further back, and what was critical, the roots for the 3rd molars were open, which showed this individual was adolescent. The roots of the 3rd molar being open showed it was adolescent and not adult, as Robert Broom had said. We went one step further. We said Mrs. Bliss wasn't female, that it should be called Mr. Bliss because it was male. If you look at the top left of this image of Mrs. Bliss, you can see a protrusion which is called glabella. Glabella is most prominent in Mrs. Bliss as compared to all other specimens of Australopithecus africanus. And that glabella indicates that Mrs. Bliss was male, an adolescent male. So instead of Mrs. Bliss, it might be called Mr. Bliss or even Master Bliss. We have confirmation of this, although my lips are sealed because we have new evidence from micro-CT scans. This early scanning program was done in the early days using a medical scanner. Now we have a micro-CT scanner at my Evolutionary Studies Institute at the University of the Witwatersrand, courtesy of the Ministry of Science and Technology, which have supported paleontology in a big way within the last 20 years. And this is an exciting image. This is not the real brain of Mrs. Blaise, it's the virtual brain of Mrs. Blaise. Based on our CAT scans, we could develop a virtual endocast looking at the impression of the brain. And what was most exciting was that there was asymmetry on the left side of the brain in the area of Broca. And Paul Broca had recognized a region of the skull of the brain in modern humans that related to language. And having recognized it in Mrs. Blaise, more than 2 million years old, we could say that Australopithecus africanus must have had the incipient capacity for speech, which was really exciting. And the late Phillip Tobias had shown that Homo habilis, a little younger, at about 1.8 million years, also had an expansion on the left side which related to Broca's area and the capacity for speech in Homo habilis. We don't have only Mrs. Blaise, we have a skeleton that was found very close to it, and I like to think that this represents one individual. So that was one skeleton of Australopithecus. There's been another very exciting discovery made more than 20 years ago, but this is a fossil called Littlefoot. Littlefoot was an individual of Australopithecus prometheus that fell into the Stokefontein caves and couldn't get out and died within the cave 3.67 million years ago. This discovery was made by Professor Ron Clark and his two assistants, Nkwani Molefe and Stephen Motsumi. And credit must be given to all three for making this remarkable discovery. This is what I did with Ron Clark and my French colleagues. We simply used a laser surface scanning technique to plot out the distribution of the skeletal elements of this individual, the poor Littlefoot, 3.6 million years old. You can see the hand, the Stokefontein hand, and not a poker hand, as Sidney Brenner described to us yesterday. This is the hand of an actual fossil, held up like this and slightly separated from the rest of the body because of slumping in the deposits at some stage. And there's the skull in the middle and the other elements further apart. Now I will talk briefly about Kromdraai, which is the cave where I've been working for many years. There's a travertine deposit which separates two layers of sand, and we can date those deposits using magnetic signals to 1.95 million years. And this fossil has been found called Paranthropus robustus, discovered by Robert Broom with the help of a schoolboy, and we've done CAT scans of it. We can look at the roots of these teeth, which are very important, helping us with classification. But it's not only Paranthropus that we've discovered at Kromdraai. In the middle, we also have Homo. Homo species. We don't know which species it belongs to, but it is similar to what's been found at Olduvai Gorge in Tanzania by Palikis and described by Phillip Tobias as Homo habilis. But boundaries between species break down as sample sizes increase. We've been working there for many years, and not only fossils have we found, but we've also found tools. And these tools have been called Oldowan, similar to the Oldowan technology from Olduvai Gorge. These are polyhedral cores, a few flakes struck off from one side. And the question arises, what were they used for? Here's a photograph of one of these stone tools, 1.8 million years old. And guess what? We did a little bit of chemical detective work. We did X-ray diffraction analysis, directing the X-ray beam on the tip of the stone tool, and we found evidence for bone appetite. The bone appetite signal was there, indicating that the stone tool had been used for bashing bone. And why? probably to access marrow, which is a good source of protein. It would have been very convenient for those hominid individuals to scavenge from the kills of leopards or lions or saber-toothed cats and get access to the marrow, which was good food. And here's an example of one of the carnivores. This is a saber-toothed cat. The hominids had to be very careful of carnivores, including leopards, which we find at the cave of Swatrans. This is where we have evidence for Paranthropus robustus as well as early Homo, whether it's called Homo erectus or Homo ergaster, going back at least 1.8 million years. And also at Swatrans we have evidence for fire, represented by burnt bones. You can see black bones, grey bones, white bones, and Bob Brain from the Transform Museum recognized these as being bones heated to more than 600 degrees Celsius, which represents the controlled use of fire. Australopithecus sediba has also been in the news within the last 4 years. Another discovery by Professor Lee Berger from the site of Malapa, not very far from Sturkentain. 2 skeletons were found, one of an adult female and one of an adolescent male. Here's the adolescent male, Australopithecus sediba, but here's the question. It's been called Australopithecus sediba, but it's got teeth like Homo. So the boundary between the two genera is not necessarily clear. And with a splash of publicity, more discoveries have been made of Homo naledi, this remarkable new species, which is in the order of 300,000 years old, from the site of Rising Star, and dated, as I said, 300,000 years. And one of the conclusions reached by Professor Lee Berger was that Homo naledi carried its dead into the back of the cave and deposited the dead deliberately. And not many people want to accept that idea because it's done in darkness, through sinuous roots, up and down and narrow, and you have to have a waist diameter of 15 centimeters to get into the back of the last chamber. So, was it really true that Homo naledi carried its dead and buried its dead deliberately? We have one way of addressing this problem. I've recognized black spots on the bones of Homo naledi, and these black spots are manganese dioxide. And the manganese dioxide could have been deposited by lichen. Lichen do in fact grow on bones in damp situations with some light. The algae component of the lichen depend on light, and the fungal component of the lichen relate to spotty distributions. There's a spotty expansion of lichen from the central talus, getting smaller and smaller as it gets younger and younger. And we found black spots on bones of Homo naledi, which told me that there might have been another entrance into the chamber, allowing for light to penetrate and allowing for the lichen to grow. That's my interpretation. So I'm proposing, as a hypothesis, that there was in fact a second entrance, so that Homo naledi didn't have to go through the darkness and deposit the bones into the back of the cave. And maybe, just maybe, the 15 individuals of Homo naledi at the back of the cave may have been a family group with a few juveniles, some adults, and a few old individuals, representing a family. To my mind, that represents a family group, and maybe a family had gone down into the cave, and there might have been a roof collapse, blocking their access, and therefore leading to the death. That's just an idea. Bolt's Farm is another site where I've worked. It's been very exciting because we have fossils that are 4 to 4.5 million years old in South Africa. And we haven't yet found hominins, but we've found other animals like Parapapio, represented by the bones there. And where you find Parapapio in Africa, you usually find hominins. So we're on the search with our French colleagues. Early hominids in Africa, well, the French were responsible for the discovery of Sahelanthropus going back 7 million years ago. There is Michel Brunet on the left, who discovered with his team the first skull of Sahelanthropus, thought to be close to the common ancestor for humans and chimpanzees. Again, the French connection reflected there by the presence of the Abbé Breuer, together with Raymond Dart and Robert Broom. We continued our work in 2001 with the HOPE program, the Human Origins and Past Environments program. And computed tomography, as I said earlier, has been very exciting, allowing us to look within the skulls and bones of fossils non-destructively. This is the kind of thing we've been able to do. Here is a mandible of Paranthropus robustus, and we can virtually extract the teeth in such a manner. And it's the teeth that are very useful for helping us with classification. Classification, in the brief time that I have left, is a thorny problem. And I have applied a certain method to various kinds of fossils using this technique. You take measurements from this skull, the orbit width of that skull, and you take orbit width of specimen B. You do the same for cranial length, cranial breadth, and you plot them against each other for the two skulls, and you get a regression line with a slope m, and what we call the standard error of the slope m, which is simply a reflection of the degree of scatter around that regression line. And the objective is to define a species in a probabilistic manner. We want to apply it to the fossils, recognizing that boundaries between species are not always clear. I've applied it to fossils from South Africa and also from elsewhere on the African continent. I've used skulls, I've used teeth, and I've used postcranial. This is what you do. You plot the measurements, you get a regression line associated with the equation y equals mx plus c. It's that coefficient m that I'm interested in that relates to the slope. When the two specimens A and B are the same species, there's little scatter around that regression line. And that's a reflection of the two specimens A and B being the same species. If the fossils or skulls of modern specimens are different, of course you have differences in shape with a greater degree of scatter. You can infer that they are probably different species if there's a high scatter. This can be applied to fossils. If there's limited scatter, you can say there's a high probability of conspecificity that the fossils might be the same species. But you need a frame of reference for assessing these results. You can take two wildebeest skulls, A and B, plot them against each other. And if you find that there's limited scatter, you indeed infer a high probability of conspecificity. But we've done it not only on two skulls of wildebeest, we've taken mammals, birds, reptiles, two at a time, plotting them against each other, and when you look at the log of the SEM, you get a log normal distribution, minus 1.61, plus or minus a standard deviation, 0.23. And to my eyes, that allows us to define a species in a probabilistic manner. Minus 1.61, remember that number. Minus 1.61, that's the average value based on thousands of measurements and thousands of comparisons, thousands of regression analyses, and we get this log normal distribution, which perhaps is a good statistical definition of a species that we can apply to fossils. If the two specimens of the fossils relate to minus 1.61, we can say there's a high probability that they are the same species. I've dared to say that the value of minus 1.61 is an approximation of a biological species constant. You know, the Hubble constant has the letter H. The species constant has the letter T, but I'm not saying it's related to any particular person. This is simply a result of analyses for 12 different hominin fossils. Some of them are Australopithecus and some of them are Homo. If one assumed that one could apply alpha taxonomy to these fossils, one would expect a pattern of black and white. But there's not. There's a spectrum of color going from Australopithecus into Homo. And that's what I mean by sigma taxonomy. Red reflects a high probability that two specimens belong to the same species. Purple reflects the fact that they have a low probability. So, in the time that's available, how much time do I have? Sure. 5 minutes, right. With my colleagues, including Caitlin Shrine from Washington, we've just published a letter published in the South African Journal of Science talking about sigma taxonomy, where S is a spectrum. Sigma is S for a spectrum of variation through time and space. And we simply used the results of various analyses to recognize boundaries aren't clear, but we can begin to draw a family tree using a log of the standard error of the M coefficient. Here we have time on the left axis, but on the right, this time going from left to right, we have a scale of degrees of similarity. And I dare to draw lines. In this case, I've just put in an oval, connecting Australopithecus africanus with Homo habilis, leading on to Homo erectus. And that little foot skull has not yet been formally described by Ron Clark, but we do have another fossil that belongs to that same species, Australopithecus prometheus, which is at the bottom. And maybe that's the common ancestor for Australopithecus africanus going on to Homo habilis. Whereas towards the left, we might have a line between Prometheus leading on to the robust Australopithecus. But this is an exciting stage of research. We are exploring the use of this statistic to draw up a family tree whereby you have a scale on that x-axis. You can apply this kind of technique to pairs of fossils or groups of fossils. The two skulls on the left have been called Australopithecus africanus. The two skulls on the right have been called Homo habilis, with a slightly bigger cranial capacity, as shown in green at the bottom, 590 cc in the case of one specimen for Homo habilis, closer to 400 cubic centimeters in red on the left for Australopithecus africanus. And guess what? When you compare Mrs. Ples on the left and Homo habilis on the right, you find when you compare those two skulls against each other, a mean value of minus 1.615. To my mind, that is telling us those two skulls represent one species. And I'm going to just end on that point. It's exciting that we are now applying this kind of technique to the fossils. It's not only the discovery of new fossils. To my mind, it's also important to develop theoretical approaches, mathematical approaches, whereby we can try to sort the fossils and classify them. I want to say that there's a word for this result, and that word is chronospecies. On the left, we've got Mrs. Pless at 2.6 million years. On the right, we've got Homo habilis at 1.6 million years. So there's only 1 million years separating those two specimens, and the mean log SEM value for those two skulls, when you compare them against each other, is minus 1.61, reflecting a high probability they are the same species, but changing slightly in the passage of time in Africa. Thank you very much.